Algebra 2, Chapter 7, Section 2, Working with Power Expressions. So now we're going to do some examples of various applications of power expressions and power functions. First, let's practice identification. Is the given function a power function? If so, identify the coefficient k and the exponent p. Okay, first of all, we have this function, which we can rewrite as 2 times x to the minus 3, which shows us yes, it's a power function. K is 2, and p, the exponent, is negative 3. B, is it a power function? No, because we have x to the first, and here you essentially have x to the 0. The power function has only one power of the input and no other thing added to it. Is this a power function? Yes. We can group 5 halves as k, and we can see that the power is implicitly 1. X to the first is x. Is this a power function? Well, let's think about using our rules of exponents. Here we subtract the powers and get x to the negative first. Okay, so that would mean that yes, it's a power function. K is 3/12, which is also 1/4, and p is negative 1. Which of the expressions below are equivalent? Okay, so we have 2 times x to the negative third, 1/2 x cubed. Well, x cubed, if we bring it up, is x to the negative third, but 1/2 is not 2. But here we have 2 over x cubed, so 1 is equivalent to 3 by the rules of exponents. What about 4? We have 0.5, which is 1/2 x to the negative 3. Well, that's the same as 2. So 2 is equivalent to 4 because 1/2 is equivalent to 0.5, and 1 over x cubed is equivalent to x to the minus 3. Okay, so 1 and 3 are equivalent, and 2 and 4 are equivalent. Which is bigger, f of 10 or f of 5? So if we think about, we have the same constant, of course, since we're looking at f at different inputs. If you remember back to the graphs in the previous section, we had when the power was bigger from 0 to 1, first we had when the power was 1, when the power was 2, we got this shape. The power was 3, we got this shape. When the power was 1/2, we got this shape. When the power was negative, we got this shape. Right? When the power was 0, we got this shape. So each time when you're going this direction from the graph, as the power gets bigger, if the power is positive, so if the power is positive and x is bigger than 1, then the values go up. So if you see that principle. So when you have power of 0, they're not going up or down. When you have a power of even 1/2, which is more than 0, it's going up. When you have 1, it goes up. When you have squared, it goes up. Okay. Only when the powers are less than 0, when x is bigger than 1, does it go down. Okay, so f of 10 will be bigger than f of 5 no matter what the function is if the power is bigger than 0. So here f of 10 is larger because the power is positive, it's 3. Here the power is kind of hidden, so let's figure this out. We have square root of 25 is 5, the square root of x cubed would be x to the 3 halves, but x is in the denominator. We have x to the minus 3 halves. Here the exponent's negative, so f of 5 will be bigger. This is also an important aside here too, is the constant k needs to be positive. Otherwise, if it's negative, we're flipping. I didn't talk about this when we were graphing, but if k is negative, we essentially flip the graphs over the x-axis because you're multiplying all the values by -1 or negative whatever, which makes the shapes opposite. And then c, we have 3, the square root of 3, u to the 3 halves, which 3 halves is bigger than 0, so f of 10 is bigger. Which is bigger, f of 0.5 or f of 0.25? So here we have several things going on. We have a negative k. Okay, we have in between 0, we're in between 0 and 1 in this case. We're looking at f of 0.5 and f of 0.25. So in between, if k was positive, and you're in between, then if the power was positive, the function goes down as you're going up, going left to right. So if we go back to the graph, so here you have positive powers. So when the power is positive, I'm sorry, doesn't matter where you are, the function's still going up, right? I got confused here. So the interval, this part's not important. The k is important. The x is not important, as long as x is greater than 0, really. Greater than this half of this part of the graph. As long as x is bigger than that, we're not looking at the left-hand side of the graph. So here, if the power is positive, k is positive, and x is positive, the graph goes up the whole time. If the power is negative, the graph goes down the whole time. It's this hyperbola shape. If the power is 0, it's flat the whole time. So that's still true. This is when we're comparing different powers, when we're looking at the interval from 0 to 1, not the same power at different inputs. So here, as constant, if the constant is greater than 0, then the power is greater than 0, and x is greater than 0, the input, or in this case t or r, whatever the input is, then it goes up. Okay. If k is less than 0, the opposite's true. You go down when p is greater than 0. Okay. So here, or if it's negative, if the power is negative and k is negative, it flips it over again. So you flip, which means you're going up. So this expression is equivalent to -4. That's t to the 1/3, and it's over it's on the denominator, so it's t to the -1/3 power. So here the power is negative, the constant is negative, and so that's this case here, we're going up. Okay, so the bigger of the two is f of 0.5. And the second one we have -5, but in front not -5. So you have -1 over 5 times r squared over r to the 3 halves, which is equal to the subtraction of these powers, which would be 2 minus 1.5, or 4 halves minus 3 halves gives us 1/2. So you have -1/5 r to the 1/2 power, which is a positive power. Since the power is positive, the k is negative, we're going to be going down. So the bigger of the two is the smaller input value, 0.25. After 10 years, the value V in dollars of a $5,000 certificate of deposit earning annual interest X is given by the following equation. V is 5,000, which represents the dollars you invested, times 1 plus X, 1 plus the rate, to the 10th power, where 10 is the years. Okay? So what is the value of the certificate after 10 years if the interest rate's 5%? So 5,000 times 1 plus 0.05 for 5% to the 10. 1 plus 0.05 is 1.05 to the 10th power. So 1.05 to the 10th power is, we need a calculator to find it quickly. It's 1.05 times itself 10 times. So using a calculator, 1.05 to the 10th is 1.6289 roughly. 1.6289. And then multiplying by 5,000, we get 8,144 and 47 cents. Is our ending balance at 10%. What about, sorry, at 5%? What about at 10%? 10% is 0.1, 1/10. Adding 1, we get 1.1 to the 10th power. So we're doing 10 years. So 1.1 to the 10th is 2.59 times the 5,000 is $12,968. $12,968.71. The amount you need to invest for 10 years at an annual interest rate X if you want to have a final balance of $10,000 is given by this equation. How much would we have to invest to get to the 10,000 in 10 years if the rate is 5%? So P is 10,000. In this case, our 1 plus our rate's 1.05 to the negative 10th. So using a calculator, we'd have 1 over, or we can just do 1.05 to the negative 10th, 0.613913, and multiplying that by 10,000, we get $6,139.13. If we have 10% interest, we'll need to invest less money to get to 10,000 in 10 years. And then we do the math on that. We have 1.1 to the negative 10th is 0.385 times 10,000 gives us $3,855.43. $3,855.43. And so you see how much less money we need to invest for 10 years to get the $10,000 value by the end.